Okay, thank you. It's recording, I think now. Yep.
Yeah, it is. Yeah.
Okay. Okay, and then yes, so section A, this is just one tab for forward, section B for backward, and you know how to create your Excel file. Don't change the X intervals. I like to just see this large number, right? And of course, you want to see that it's not really stable type of approximation or simulation. In section C, you can explain what you found during, you know, the creating your toolkit in Excel. So that's all I want. For problem 3, however, it's basically the same thing. In this case, you have, of course, more freedom, right? You define your MATLAB file, but you can also play with the variables, like the intervals in terms of the space and time. And then this is what I really want to see in section C of problem 3. So what I mean by under what condition you know the simulation or your approximation is stable is that what would be, for example, different velocities, negative, positive, what would be that impact, and then also the impact of changing the intervals in space and time on your approximation. Okay, so that was all about assignments. So I hope that you are clear. And then the due date is Saturday at the evening, 11:59, before the start of Sunday. Okay, so let's talk about these stability issues a little bit. I don't want to go into really the details, but I would like to give you some general idea of some theoretical, you know, explanation about these stability issues. So let me stop sharing and then move to my iPad. Okay, so hopefully you have started to work on your, you know, making your Excel and MATLAB files. But of course, when you are going to work on this problem, you will find that by changing the space and time grids, of course, the simulations would be different. So this guy's von Neumann, he actually worked on the stability analysis on of finite different approximations. So he just simplified the problem and said, okay, if we have this unknown function of u for the future time step n+1, we just defined this as our unknown function with the current time multiplied by an amplification. Okay, so just imagine that we have this unknown function in the future. We can approximate this by just you know, multiplication of this unknown function by a factor, and he called this a as amplification or amplification factor. Then he says that okay, if the magnitude of this amplification is less than 1, this means that my simulation or my results out of this finite different scheme would be stable, but this is basically damping. Okay, what does that mean? So just I'm getting back to our original problem of 1D advection problem. We had some pollution in our system, right? And remember that when we perform some of these backward or forward schemes, sometimes this magnitude, the maximum magnitude of the concentration, which is 1, actually would lower to some other numbers like 0.9. He says that this is also stable, okay, but this is damping. So it's, even though it's not pretty accurate approximation, but it's under the control. It's not getting really high numbers. If the magnitude of this A or amplification number is equal to 1, then this is called neutrally stable. So this is pretty close to our accurate outcome or results, right? And then if the magnitude of this amplification is larger than 1, then that's the case that we got this unstable condition or amplifying. Again, this means that in terms of our original problem, this will get higher and higher, and in some case, it will be really out of control. So this is called unstable.
Professor, does this mean that you have to choose your delta t and delta x so that they're kind of like their ratio is like the inverse of a velocity, or so that whole thing is equal to 1?
That's a little bit different. Okay, so this amplification value, you're correct actually. The amplification factor is a function of delta t, delta x, and your space and time, intervals. And yes, so we're gonna actually pick some numbers that will give us these two values. Okay. So anything larger than 1, this will be called unstable. So we are going to basically pick the best out of those delta x and delta t to satisfy this condition of stability. Exactly. But it's a little bit different, so I'm going to explain about it. So this guy, von Neumann, actually worked on the theory of this amplification factor. I don't want to go to the detail in this lecture because we have to work on the Fourier transformation. But then using the Fourier transformation, he found this amplifier. And then at the end, as I said, he found that this factor is a function of delta t, delta x, and the velocity. And I'm just talking about this special case, right? The advection problem. Of course, in other problems, this amplification factor would be different. And then he found that really this factor is v times delta t divided by delta x. I think this is familiar to you, right? This is the factor right behind your equation. So this u, I think n plus 1, this is how we wrote the problem, would be I at n, and then this is minus v delta t divided by delta x times some other approximation. So this is really the amplification factor. So how he found this, again, this is through Fourier transformation. We may actually work on this in the next lecture. I don't want to go to the details because you need some background. Okay. And then he defined the stability criteria. So this is the stability criteria. For forward in time, of course, as I said, in time, we are mostly working on the forward because we like to predict the unknown function in the future, right? And backward in a space, he found that if the velocity is less than 0 or negative, can you say if this is stable or unstable?
Be stable because A is less than 1, right?
This is less than, this is V. Okay, I'm not just talking about the amplification factor, okay? Because I didn't actually talk about delta t and delta x. This is just about the sign of velocity. Okay.
Would it be?
Okay.
Yeah, any other thoughts?
It would
Would it
be
be
unstable.
Unstable, exactly. And this is what we actually work on that on last lecture, right? We talked about this upwind method, and upwind means if velocity of our field is negative, we should find a different scheme which is in opposite direction for the velocity. So this velocity is negative, is basically, we can say that this is backward, right? So we don't have to we must use another scheme. For this backward scheme, this should be unstable. This is one criteria, but he also found that if other criteria, so or this amplification factor, or V times delta T over delta X, if this gets larger than 1, this is also unstable. So what does that mean? Even if velocity is larger than 1, I mean larger than 0. So if let's say that velocity is positive. In terms of the velocity, this should be stable, right? But then even in this case, if this term or amplification factor is larger than 1, then your simulation will be unstable. Okay, so I think you have a better idea how to change your delta t and delta x in your assignment 3 to get stable conditions. For your assignment, because I didn't cover this von Neumann stability analysis, I don't want you to use exactly these numbers. I'd like to ask you to just perform some try and error, okay, by changing delta t and delta x, and see what would be the number that you can get to get an stable condition. Okay. So that's about FT and F. I mean, forward time, backward in space. We also can define the stability for the forward method. So in this case, if velocity is larger than 1, right, so this means that I'm going to have the same direction. And of course, this means that I have unstable condition. This is the same. So if V times delta T divided by delta X is larger than 1, then again, I'm going to get unstable results. And this is interesting. You see that this amplification factor, so we have delta T and delta X. This means that even if you decrease delta T and then apply some decrease for delta X with same rate, you are not actually changing this amplification factor, right? So what is more important in this case is getting something less than 1, right? And this means that we need to decrease this delta T and maybe do not increase or change the delta X too much. Okay. So this is about the stability. We're going to work on the theory how we can actually find this amplification factor for more complex problems. Any question? Okay, so this guy again doesn't mean necessarily that you have to decrease delta T and delta X simultaneously. That's the lesson. Okay, I think we are ready to move one more step further and work on a two-dimensional advection problem. This will be a more interesting problem because it's closer to an actual case in the field. Okay. So let's work on two-dimensional advection. And this is pure advection. I think we're going to get some time to work on a pure diffusion at the end of this lecture. So what does that mean? Again, if you remember the equation of the advection, we have the unknown function, first derivative with respect to time, and then negative times the velocity times unknown function, first derivative with respect to x. This is 1D. And then we're going to add one more variable, which is our unknown function, first derivative with respect to y. This is 2D advection problem. This is a specific equation where this velocity basically is same for x and y direction. So a general form would be ut is equal to minus velocity in x direction times ux minus cy uy. So what does that mean? For example, let's say we have a domain, some concentration or pollution exists in your system. This means that we may actually have some flow field like this, and this has some component, right? In this case, the velocity in x would be different from the velocity in y direction, right? So this is a more general form for two-dimensional advection problem. Okay, so let's see if we can write the discretized form of the finite difference scheme for this 2D advection problem. Can you help me to write the approximation for UT in discretized form? Let's use a forward. Okay, so I'm just trying to approximate this for forward in time and forward in space, and space here means forward in both x and y. So now I'm just working on forward in time. Let's try to write down the approximation for our unknown function. So what would be the approximation?
UN plus 1, I think, for the
Correct.
time.
Yep.
Plus UN.
It should be minus, right?
Yeah.
Okay.
Actually, let me go back to my notes. I'm not sure.
Right. And then this should be divided by delta t, right?
Yeah, it should be divided.
Almost, right? But this is a two-dimensional problem, so the indexes for x and y should be constant, right? So we're going to have I and j because we are approximating for time. Nothing would be changed for the space. Okay, so this is an approximation for unknown function with respect to t. And we have almost the same thing for approximation in space, right? For u to x, this should be... Okay, can you tell me this one?
So it should be UI plus 1 J UN
Exactly, okay.
minus UI J M over delta X, I think.
Exactly. Thank you.
Yeah.
So this is the approximation for ux, and of course we're gonna have exactly the same thing for uy, but forward in the j index, right? I j plus 1 and minus u, and I, this should be j divided by delta y. So this is forward in time, forward in space. Okay, I need to resize this, guys, a little bit. FTFS. So we have everything, right? We need to approximate these three terms, and we already did. And cy and cx are constants. Okay, so let's try to write down all the approximation for the variable that we are looking for. So what's the variable that we are looking for? What is this function? I mean, which one we are interested to write down our equation for? Actually, we have to write for
ui j n plus 1, I think, right?
Yes, this guy, right?
Yeah.
Exactly, because this is our unknown function for the future. So we already should be able to find everything in our current time, right? In the current time, but what we are looking to predict is the unknown function for the future. Okay, so if you rewrite everything for this ui and j at n plus 1, then this will be your final equation. So actually, I substitute all these ut, ux, and uy in my 2D advection problem. That's all I did. It's pretty similar to what we had before, except we have one more term in our 2D problem. Okay, this should be I, J, N, right? And then minus, this should be C to Y. I mean, velocity in Y direction, delta, this should be delta Y. And then approximation in Y direction, or I, J plus 1, N minus U, I, and J, and N. Clear, right? Any question? Okay, so let's see what would happen in terms of the grids in space and time. So in 1D advection problem, we had a grid system just in 1 dimension, right? In this case, we have a grid in 2 dimension. And let me just draw a very simple grid system or mesh grid with just 5 or 4 different intervals, right? So in this case, I'm gonna start with the index of x direction, I, so 1, 2, 3, 4, and the other numbers, this is the x direction. And then on the other hand, I'm gonna have some y direction, and these are the index for j. So the grid that I just draw, let's say these are the unknown functions right at the first time interval. So this is just valid for t equal to n. And let's say this guy right here, what should be the discretized form for this? This is u at I equal to 4, right? And j equal to 3, and the time of n, right? Because we are actually standing on I equal to 4 and j equal to 3. Please. Okay. Okay, so what would happen for the next time step? We're gonna have exactly the same space grid, right? But then this is for time equal to n plus 1, right? And then this guy will be just u, 4, and 3, n plus 1. So we are just extending 1D to 2D, right? In 1D, we had the grid on just x-axis. This was for t equal to n, and then, you know, other unknown functions for the next time steps. Here we're gonna have a 2D grid, and then this will be extended to the different time intervals, right? Okay, so let's see what would be look like in different times. I think if I present this in a different representation, that will be nice. Let's say this is my 2D grid. I'm just drawing this in 3-dimensional view. Okay, so this is my 2D grid. And then let me just pick a color like green. This is my first interval. All the unknown function will be calculated on this time interval, right? This is space grid at time equal to n. Let me copy this, and then we can predict the values for the next time steps. So this is in time. And maybe it's better to pick another color like this orange. So these are all my future predictions. Next time step, next, and then so on. So we are basically moving from time step n to the next time step, and next, and next. So can you tell me why I pick a green for the first layer and different color for the future predictions? What is this green about?
Advection, yes.
What is that?
No advection, yes. So the polluted material is green. I think that's why.
No, it's not about the advection or diffusion. This is only the first time step. Okay, so think about the time steps. Why the color of my unknown function and this space grid is different from the color of the other space grids, time grids.
Because you use a different formula?
No. Okay, so I picked actually green because we're gonna need some initial conditions, right? So these are basically known variables or known u's because we are at the current stage of time, right? So remember from 1D advection, for the first time grid or time step, like t equal to 0 or 1, all these points or unknown functions, this has to be actually knowns, right? We're gonna have some measurements before starting to have the prediction. And this is actually our initial conditions. So in this case, for the entire space grid, but at t equal to n, I mean the first time step, let's say 0, all these unknown functions or variables, these are actually knowns. Okay, so we need to know all the magnitude or the values for these u at t equal to 0. Okay, so let me take a copy from our approximation formula, put it right here, and then draw another grid like this. Maybe I need to draw one more. This is the space grid in time equal to 0, or the first time interval. Doesn't matter how many grids you have. And then we are going to predict this unknown function for the next time step. Let's say I'm interested to find this unknown function at t equal to n plus 1, and we have the unknown variables for t equal to 1 to n. So can you tell me, to predict this point, this red point, what other points I need from the previous time step? Just look at this equation, right?
Yeah, so we'll need j plus 1 and I plus 1.
Yes, I plus 1 and j plus 1. So let's just actually mirror this point right into my previous time step, right? So what I need, let's see. We're gonna need exactly the same thing, which I just plot with this red point, right? What else? This is exactly the same, and this is the same. So let's say these are the center points. We're gonna need one more point. This is forward in x, so this should be the point, right? With the same j. And then there is another guy, which is this one. So I just need these 3 points, right? These 3 points is just needed for ft forward in a space for my 2D advection problem. Make sense? Okay, so one more question. What would be my ghost points? So remember that we need some ghost points, right, for the approximation in the boundary conditions. So can you tell me in which limits in x and y we need to have these ghost points? Just think about the marching, right? The sweeping or marching methodology. We have to predict all these unknown variables from the first point and then go right. Once we finish the first row, we're gonna sweep, right? And then calculate the next row. So what would be the ghost points that I need for the approximation?
Would it be on the top and on the right?
Exactly. Thank you. And that's because of having this approximation, right? So in order to get this value, I'm gonna need to project this to previous time step, and I need 1 point on top. Let's say above point, and then I need 1 more point on the right side, right? So let's say I'm just standing on this point. I would like to predict this. This is fine, right? I just need this point above and right. That's not a problem, right? But then once I get to the very end, to the right point, right? I need this point, above point, and this is the problem, right? I'm gonna need another point on the right-hand side of my boundary conditions. So this will be my first ghost point. And this would happen for the other points on my right-hand side. What would happen if I actually like to predict the value on this grid point? I need the center, above, and right, correct? So again, this will show me that I would need some ghost point on the top limit as well. This is more like an octopus actually than a ghost. But anyway, this is our ghost points. So you may realize that by changing these forward, backward, and even central schemes, well, your ghost points would be different, right? So can you tell me, if I use backward in space, what would be the ghost points?
So your backwards in space would be like your negative y and your negative x, so left and bottom.
Exactly. Thank you, Eric. Exactly. And what about central? If I use central method.
All of them.
Correct, exactly. So in central method, your future point, you need to project this. Actually, you don't need the center point, but you would need left, right, above, and bottom. You don't need the center. And then you can imagine that in all the boundaries, left, right, up, above, and below, actually you need these ghost points. Okay? Any question? Okay, so let's work on another example. Let's make our previous example a little bit more complex. We're going to move to a two-dimensional problem. Let's say, actually everything except some initial condition would be different, would be same. We're going to make a toolkit in MATLAB. I think it doesn't make sense to use Excel anymore. Okay, so two-dimensional, you have to make these grids and then copy and paste these grids for each time interval. So as you see, this doesn't make sense. Actually, you can write some QBasic type of scripts in Excel, but as MATLAB is more easier, we're gonna just use MATLAB. This is a two-dimensional pure advection problem. And let's extend our domain to a 2D domain. Previous case, we had really a long river, but in reality, even a long river would be a two-dimensional problem, but we just assume that this is, the longitude is really longer relative to the width of the river, and we assume that this is a 1D advection. But here, let's just assume that we have a square domain. Let's see, it's just a section of a lake or an ocean. The dimension, this is 200 meter in X and 200 meter in the Y direction. What about the pollution or the initial condition? Let's just assume that we have some interesting pollution in terms of the concentration and its geometry or the zone of impact. Let's just assume that we have a square zone of impact for this pollution. The center of this square thing, pollution, is at 50 meter. And then let's say this is the origin, okay. And then 50 meter for the y-axis. And then this is 20 meter long and 20 meter long in both X and Y direction in terms of the concentration. The concentration of the pollution is equal to 1 at maximum. So let's build this MATLAB tool for two cases. Let's say for case 1, we have a flow field. The velocity in X, or let's just write V. V and C are same thing. Velocity in X direction, this is not derivative, right? I mean, velocity in X direction. This is equal to 1 unit meter per second. And also the velocity in Y is equal to 1. So you can imagine that our flow field is in this direction, right? The component of X and Y are equal. And then for the second case, let's change the velocity field to exactly the opposite direction, -1 and -1. Number of intervals in X, let's just pick 200. This is number of intervals, not the number of grid points. And the same thing for the Y direction. The maximum time of simulation, let's say 50 seconds. And then delta t equal to 0.5. So we are going to simulate the pure advection, and let's see what would happen. So I think you can imagine, I mean, about the analytical solution of this, right? We have a pollution, the impact zone is like a square. So in reality, if we have a flow field like this square should basically move as a bulk concentration to this point, right? This is for the first case. For the other case, should be exactly in the opposite. Let's see what would happen if we use some finite different approximations. Okay, so if you're ready, we can actually move to MATLAB. And it would be great if you can just follow me step by step and write your script with me. Okay, just a second. I'm gonna open my MATLAB code. It may take a few seconds. So Eric, do you have any news about the stock market? I know that the Reddit army, they push for silver, right? After the GameStop.
The last I heard is they're holding the line, right?
Yeah. And I heard that Elon Musk actually today he removed the Bitcoin from his list and added another crypto type of currency.
Did he really?
Yeah, the Dogecoin or something like that.
Dogecoin, yeah.
Yeah.
We have a down payment for a house sitting in the bank right now, and I knew that was starting like really early on, and I was so close to like calling my wife and being like, "Hey, let's do it," but I didn't.
Cool. Okay. Good luck. Anyway.
Yeah. Thanks.
And actually, I'm not a fan of football, but I know that there's a Super Bowl on Sunday, right? I hope that none of you have these Super Bowl parties on Sunday. Okay, let me share my MATLAB. Something is wrong. Just a second. Screen 2. Okay. Just trying to make sure that I can see the chat panel and everything. So if you have any question, I can see it. Okay, so can you see my MATLAB screen?
Yeah, I can see it.
Okay, nice. Okay, so this was actually our previous example, right? We worked on forward time, forward in space, one-dimensional advection. And you will see that actually when you have a script for even a very simple code or problem, you can extend this for more complex problem very easily. So let me just write this. We're gonna work on a two-dimensional advection problem. So I'm gonna just edit some portion of my script, right? Okay, so velocity, as I said in our problem, should be equal to 1. X-min, it's 0. This is correct. This is the minimum value of x, maximum value for x, and then the number of space intervals in x direction, right? So of course I need to add something for my second space, right, which is in y direction. And it's pretty simple. Just copy this section and paste to add for y, right? And I'm just gonna modify this for y max, and number of intervals in y. As this is actually a symmetric kind of problem, everything should be same. Maybe you need to just modify the descriptions, right? So this is all I need to do for the input parameters. Do you see any other section that I need to modify in this one? I don't think so, right? This is all. Okay, so let's move to discretization. Of course, we need to discretize this for the y-axis as well, right? So again, this should be pretty easy. Just copy and paste what we did for x, and then modify this for the y direction. So this should be y max, y min divided by the number of intervals in y direction. For y, we need to also define discretization from the ghost point. For the left-hand side, if you can remember what we talked about for forward method, there is no need to have the ghost points in the left boundary, right? So in this case, we're going to just start from the minimum y. We're going to add the intervals by this dy, and then make our discretized system up to y max plus dy. And why we have dy at the right hand side? Because we need to have some ghost point, right? So this is plus dy for ghost point. Let me just modify this. So this is about the discretization. Do you see anything that I need to modify? Actually, there is one more thing to modify. Can you tell me what is that? So this is fine. Discretization in space. Yes, go
We
ahead.
need to add in y, I think.
What is that?
Number of intervals for y.
Actually, we already did, right? So this is discretization in y-axis.
Yeah, sure.
Time steps, this should be fine. This is just talking about the time, right? But then what about this one? This is our unknown function, right? So here the unknown function is just a function of time and x, right? And we have to add another space. This is a 2D advection, right? So we need to add for the space grid in y direction as well, and this should be ny plus 2. And y we added one more to nx plus 1. So nx plus 1, these are our physical grids, right? So remember that this nx, this is a number of space intervals, not the number of grids. Number of grids will be number of intervals plus 1, right? So this will be your physical grid. And then just by adding one more point, we're gonna actually count for the ghost point. So this is for x and this is for y. So I'm gonna actually modify this a little bit. So instead of having this u in this form, I'm gonna change the position of the time to be on the very last one. Okay, so it doesn't change anything. However, in MATLAB, when you create a three-dimensional matrix, so remember that this is in the form of matrix, right? This is talking about the rows, this is talking about the columns, or other way around basically. But when you create a three-dimensional matrix like this, So 2 dimension for space and 1 additional dimension for time. MATLAB actually can just plot the 2D dimension, and you're not actually able to see the entire 3-dimensional matrix. I'm going to show you this. So in this case, we're going to actually change a little bit the form, move the time to the last index, right? And then put the space into the first row and columns form. And this will be the 3rd dimension, which is talking about the time, okay? So let me just remove this. It's basically the same thing. We just a little bit change the form. Let me actually stop here. So if you click, left click on these lines, you can actually stop the program and just run the program up to this point. Okay, so let me just run the program to see if everything is going well. Okay, so we have everything, right? I'm just gonna click on the U. This is, initialization of my unknown function. Let me see. As you see, it says that cannot display the summaries of the variable because this is a 3-dimensional matrix, right? So if you like to see what's going on here, basically you have different time steps, right? So I can actually define something like U. This is my unknown function at some specific time. I just call it UT, right? This is equal to my U, my unknown function. I'm gonna just try to plot this for all my unknown function in X. So as you remember, we can use this colon type of symbol, and this means everything on X, everything on Y, and for a specific time. I'm gonna just pick at time equal to 1. This is our first time interval. Okay, and then semicolon because I don't want to see everything on my command window. Let's see what would happen. So it will create another function like UT. Because this is a 2D at this moment, I just picked one of the dimensions in time. So it can actually present now for UT. So you see this UT, this is my unknown function at the time equal to 1, or my first time interval. As you see, everything should be 0, right? So these are talking about X, and these are talking about the unknown function on Y, right? Okay. So this is how you can actually check if everything is going well in different time steps, because you cannot actually plot or see your 3-dimensional matrix inside your workspace. Okay, this is not doable unless you change the time to be in 2 dimension. Okay, what about initial conditions? So I changed the initial conditions a little bit. We are not going to use this normal distribution anymore, right? It's the pollution or the concentration of my the density of the liquid is basically a square, and then it's all equal to a constant value which is equal to 1, right? So that the value would not change, it just depends on the space. So how to create this type of set, initial conditions? I'm gonna just create a loop to define these initial conditions. Let me, if I can grab this. Okay, I think this is better, right? You can see what we defined. So this is our initial condition. So I'm gonna create a loop to search for these special points and then implement the concentration into these points. This is all I'm trying to do. So the first for loop, this is for sweeping in X direction, right? So if, for I equal to from the first point to the last point, right? Remember that this is our last point. This is the first loop. We're gonna also have to sweep for the other space, which is in X direction. So from 1 to ny plus 2. So I'm basically searching all these grid points, and once I reach to the point that is inside this domain or this impact area, then I'm gonna put some concentration into it. This is all I'm trying to do, okay? So we need to put some condition, right? The condition is if my x, right, this is the value of the x, right? I need to define the index as well, right? Because this is just index numbers. The value for x should be defined by the index. If this is larger, then can you tell me how to write this condition? Let's just think about this zone of impact. What should be the x value, the condition for x? It should be started from this point and then ended at this point, right?
So it's going to be from 30 to 50.
30 to 50. Well, basically the center is 50, and this is 20, right?
Like 40 to 60.
Yeah, so
40 to
40 to
60,
60.
exactly. So it should be larger or equal to 40 and less than 60, right? So in MATLAB, this is how you can write and. So you have to actually write down two ampersand, one right after each other, and this will define kind of an and if condition. And then this should be less than or equal than 60. So this is the condition for x, right? And we're gonna end the if condition. We have to actually define another if condition inside the first one, right? Because this is not the only condition. So what happens if x is larger than 40 and less than 60 but for example y is in this region, right? This is not acceptable. So we have to define exactly the same thing, but for y direction. Make sense? Okay, and then let's put our unknown function. This is our initial conditions, right? So anything in my unknown function which has these conditions, satisfy these conditions. So I, j, and at the time step of 1, this is my initial condition, right? This should be equal to 1.
Do we need to change the I to J in the
Okay,
index for J?
Exactly. Thank you. Thank you, team. Okay, so this should be fine. Let me stop the program up to this point and run again. Okay, so there's no problem. It's fine. And let's just check, make our UT again. So if you actually push your keyboard, the upward, the arrow, you can see all the scripts that you wrote actually before. Okay, so I'm gonna use this guy, ut equal to u. This is all the unknown function at time step 1. So let's see what would happen in this case. So of course I should see some, values with 1 around 40 and 60, but these are actually the number of intervals. These are not actual x-axis, right? So 40, let's see when we can see this values of 1. Okay, what is our ny is 20, so it means that each, actually 40 and 60 should be exactly this, almost the same thing, because each space grid would be equal to 1, right? Okay, you see? So we actually created some concentration or pollution in our matrix. So this is how you can actually check. It's not very efficient, so I'm gonna show you how you actually can see this through a contour plot. Okay, so for 1D problem, we actually could plot this in terms of you know, a curve, right? In this case, it's not doable. It's a two-dimensional problem. So let's plot this in terms of a contour. And this is the script that you can use in MATLAB. Contour. And I'm gonna just plot my unknown function for all the unknown function on x and y, but for just the time interval of 1. And I'm gonna stop the program up to this point. Okay, so let's see what would happen. And this is the plot. So you see we got the concentration inside this point. And you can actually make this more sophisticated. So as you see, you know, the scale in x-axis and y-axis are not equal because of the presentation. So how to fix this? You can actually write this script axis equal. An axis equal means it will actually make the axis in x and y at the same scale. So if I run the program again, this is the plot. This is much more better than before. One more modification. You can also add the color bar. Let me actually start from this modification. If you write another F at the end of the contour, it will actually fill inside your contour. So let me show you. This is what you would get if you add an F. An F means fill with some colors. So you got some higher concentration inside your pollution, and then the concentration outside your pollution would be exactly equal to 0, right? You cannot see the magnitudes, so let's do one more modification. This is the script that you can use, color bar. And let me tell you actually something. Maybe about 10 years ago when I started to write codes in MATLAB, I didn't know anything about these codes. So anything that comes to your mind, you can just Google this, and there is a MathWorks forum that can actually answer all of your questions. You can find the solution. So for example, when I plot this contour F, I found that I don't have the magnitudes, right? So just Google how I can see the magnitude on the contour F, and then it will be directed you to this color bar. The other way around is that in this section, let me see if I can extend this. If you push help, it will direct you to MathWorks, and then you can also write your question here. Or let's say you know the function, but you don't know how to use this, right? So let's say color bar. And then there are a lot of information about this color bar. So you can see how you can use the color bar to show the bars, or even set different limits. Anyway, any question that comes to your mind, you can search on help, or of course Google this. Okay, so let's add color bar. This is a modification, right? So you can see that the maximum is 1 and the minimum is 0. This is nice. One more modification. You can also change the color map. So what does that mean? Let me just search on the help to show you what are the different options. Color map. So this is just talking about the color maps, because you can change and actually the frequency of the colors, or the value of the colors that you are using in your contour F. If you go to really the bottom, you can see the different options. So for example, in the thermal conductivity type of problems, right, for advection diffusion problem for temperature, we're going to use the hot system, right? So in this case, the maximum color for your unknown function would be black, and then it will be decreased to white, right? So this is the color scale for the option of hot. For fluid flow problems or even for concentration, we can use this jet option. So jet means the maximum unknown function value would be from blue, and then back to the green, yellow, and to the red. So you have really a wide variety of the options, up to you, but let me just use this jet option. Let's see what would happen if I add a color map of jet. So this is the modification, right? So maximum value from red to blue. Any question? Okay, so we're getting closer to the solution of our problem. We define the contour F so we can see if everything is going well. We don't need this value anymore, right? This was just for normal distribution of our initial condition for the last problem. We don't need to plot this anymore. We may actually need to change the limit of our plot later, but let me just remove this. Okay, so from the top, again, input parameters, discretization, initial conditions, and this is the time that we have to get into our approximation. Let me put our approximation here. I think one more back. Okay, so this is our approximation. I'm just putting the equation in front of me so there would be no mistake in the approximation. Okay, so we're gonna start from the first time step and then predict everything to the last time step, right? We have to define some ghost points. The ghost point for the x direction has been defined, right? So this is ghost in our on x direction. Of course, I need to define some ghost on y direction. Can you help me to write the code? Ghost points for y direction. And actually, we have to modify this, right? Because this is for 1D problem. So the first index, this is for time, this is for x. Because we changed the form, x should be at the beginning, right? So this is my x. This is time. However, we need to add y as well, right? This is just the ghost point for x direction, so there would be no change in y. So everything in y. Right, so we're gonna add these ghost points for all the j's at the end of x direction. Right, let me see if yeah, so we are talking about these ghost points, right? So we need to add all these ghost points for all the j's, but at the end of x direction. Okay, so same thing for y, but this is for these points on the top, right? So this should be for all the x direction grid, and y plus 2, right? So ny plus 2 is these guys, these ghost points. This should be equal to their value from the below points, which should be the same thing, but just one index back. Does this make sense? If this is confusing or anything, just let me know. Okay, so at least I know that something is wrong. Of course, actually, you have to practice this, okay? So I'm writing everything out of just on top of my mind, but you have to practice this to be comfortable with writing the codes in MATLAB.
Excuse me, you didn't change the RHS on the x direction for the ghost point.
Okay, for the ghost points.
In the x direction.
Exactly. Thank you. Thanks. So I have to modify this. It should be exactly the same thing, but one grid back to the left. Thank you. Okay, so ghost points defined. Let's just sweep the space. Okay, so this should be FTFS, forward in space. This was our 1D, marching. Of course, I'm gonna need to march on the y-axis as well. So I need to add one more for loop, right? This should be J from 1 to nx plus 1. So why I didn't actually sweep to the very end, to that ghost point? Because I need to calculate everything for my physical points, right? Ghost points, they are just some points to help us to predict our physical points. So don't need to go to the very end, just the physical points.
Would it be NY?
Yes, thank you. Exactly. Okay, so let me actually rewrite everything from the beginning. Okay, this is better. I'm just looking into my equation right in the left and then try to write it down. First index should be for x, right? So I, j, this should be n plus 1, right? The next component is this guy. So I, j, and n. Minus the velocity in x. This is what we defined, right? Let me see. Okay, so actually we need to modify this, right? There is one velocity field for x direction, velocity in x, and then the same thing for y. Okay. So you see, if I click on this, it will make it blue. It means that we have used this before. And then this is where we use this Vx, right? Okay, this Vx times delta t divided by delta x, and then times. Okay, so I'm writing this guy. It should be u, I plus 1, j, and n. Almost the same thing, but with just I, right? And this is also nice. If you click, just left click after your parentheses, you will see that there will be an underline under your parentheses. And this will show you where this parenthesis actually is closed, right? So in this case, you can check if everything is writing in a good way. Okay, the other component is almost the same thing. So I'm gonna just copy and paste the entire thing, but then modify this for y direction. This should be Vy. Need to change dx to dy. The forward will be on just j, and this is the same thing, right? I think this is correct. Do you see any flaws? I think this should be fine. Okay. All these points, we don't need actually these lines. These are just plotting in 2D dimension. So I'm gonna just actually copy and paste all the contour plotting. The only thing that I need to change is this 1, right? So if I put 1, it means that I'm just plotting for the time interval of 1. So I'm gonna change this to n. For each time interval, I will plot the contour f. So if you run this, you're gonna see that because this is inside a for loop, it will not show you the contour f until you stop the for loop. But if you write another code like this HG, it means that show the graph. Then it will show you everything inside even the loop. Okay, so let me see if we can get some real-time animations out of this. I'm just trying to clear my workspace. Okay. Let's just check for one more time if everything is going well. Ghost points, marching in space. I think it should be fine. And as you see, the time step will be started from 1, right? So in the first for loop of time, I'm gonna actually plot for n equal to 1, you see? So there is no need basically to plot everything on top of my for loop before starting the for loop. It will be already plotted in my for loop. Okay, so this is actually the result. Is this stable? No, right? So you see that it's even going backward. The values, look at these values. 10 to the power of 45. And these are the concentration, right? So it's not stable. And why this is not stable? This is forward in space, right? And then we are using some velocity which are in the direction of our forward finite difference scheme, right? And by von Neumann stability analysis, this is not stable. So can you recommend me something to make this stable?
Can you just switch the velocity to negative?
Exactly. So this is actually section B of your problem, right? So remember that, and the example that I introduced to you in section B, we're going to work on the opposite direction of the velocity field, right? Let's see if this is working for -1 and -1. So this is the result. Interesting. So our concentration, which was right in this position, is moving in the right direction, right? And it seems to be stable. So let me run this one more time. And you see that the concentration is decreasing a little bit, which is damping, right? But it's stable. So you can basically change these variables to see what would happen. Okay, so let me change the delta t to 0.1. So it seems to be more stable, right? The shape is in the shape of a square, but then after some advection, we are still in a square shape, so it's almost stable. And it's moving to the right correction. Okay, so let me stop this. You can actually just push the pause, right, and then quit debugging. Okay, so what would happen if I like to use this positive velocity? How to get a stable condition? What's your recommendation?
Switch the scheme to forward, backward.
Exactly. So we need to switch the scheme to backward, right? So how to do this? Everything should be same in the input parameters, of course. For discretization, as you see, we're gonna need actually some ghost point, not at the end, right? So backward, let's say we're gonna apply backward in X and Y. So for the ghost points, we're gonna need the ghost point not on these points, but on the left and the behind of my domain, right? So probably you need to subtract this by dx. This is going to the left, even behind 0. This should be minus dy. You don't need any ghost point on the right. Dy should be fine, dx should be fine, and steps, everything is same. The number of x and y grid points should be the same. Initial conditions is exactly the same. You're gonna need to modify this a little bit, right? So in the ghost point before, this is right limit. So what would be this one? Can you tell me how to modify the ghost point for the backward scheme?
In x minus 2.
Okay, so actually the indexes in MATLAB always start from an integer number. So it should be always started from 1. Okay, we're gonna shift actually minus 2 to 1, okay? So you are almost correct. So 1 should be equal to what?
NX.
Okay, so
0.
let me...
0, sorry.
Okay, so we are talking about this point, for example, right? This is our ghost point, which is 1. So this should be equal to 2, right?
Okay, yeah.
So for example, for this ghost point, we're gonna actually assume some values for this ghost point, which we are just borrowing this value from the closest point, right, which is in the left. For this ghost point, we are borrowing this value from the closest point, which is on the right. So 1 should be equal to 2. This is a ghost on x direction. Okay, what about the y? What would be this one? So the ghost point in this case, we are working on backward. It means that we're gonna have some ghost point right here on the bottom of my domain. This is exactly the same thing, right? It should be 1. This is the index of my grid point at this point. It should be equal to the closest point, which is 2 on J. So we define the ghost points and marching in space. Everything should be almost the same. However, this is a backward scheme, right? So remember that the first item should be I, and then we should subtract this from I minus 1. Just get back to your notes and see how the backward method works. And again, this should be J minus 1. I think we are ready to run the program. Okay, let's see what would happen in this case. And I put the velocity to 1. Okay, where is the plot? I don't see anything. Okay, so we got a problem. Index in position 1 is invalid, and the error is in line 50. If you just click on line 50, it's going to direct you to line 50. Okay, so what is the problem? Okay, this is a problem, right? So we actually march from the very first point to not the last point. In this case, because this is a backward in space, right? Remember that the marching should be on physical points. In this case, my physical point will be started from 2, right? Because the index of 1 is reserved for the ghost point on the left and the below points. So we're going to start from 2 and then end it at the very end on the right. I hope this makes sense. And then run. And this will be your result. And this is reasonable, right? the velocity is positive in x and y and it's moving, the concentration is moving in this direction.
Hey, Professor, I had a question.
Yes, go ahead.
So is this going to be common moving forward that if we want to know something forward in space, we're going to model it for backwards in space and then reverse the velocity?
No, so actually for the pure advection, we have to use some stability analysis like the von Neumann that I show you, right?
Mm-hmm.
And then by this kind of stability analysis, before actually writing the code, we know that if the velocity is positive, we have to use an upwind method. It means that we have to use backward scheme.
Okay.
Okay.
All right.
Okay, and Giovanni, you asked what exactly do you look for to determine if it's stable or not? So I think I briefly explained this before writing the codes. Von Neumann method, it says that if your unknown function, let's say, or a concentration, right, the maximum value was 1. So if I get some value larger than 1, this means that it's unstable, right? And it's exponentially actually increasing. It's amplifying. So this is not stable. And this is just after how many time? 50 seconds, right? So if you continue, the pollution would maybe escape from the medium. Okay. Any questions? Yeah, go ahead.
Yeah, can you explain again why did you start in the initial conditions from nx plus 2 and y plus 2?
Yes, sure. I think it's better if I move to my iPad. It's going to be easier to explain that. Just a second. So one more page. So when you create actually any matrix in MATLAB, your index numbers should be always integer. Okay, you cannot say, for example, u minus 1 and minus 3. This is not acceptable by MATLAB. It should be started always from 1 and then ended at some integer number. Okay, so let's say we have this grid point. And I'm using forward scheme, right? For forward scheme, I need to have some ghost points on right and some ghost point on top. And let's just speak about this simple grid, which I have how many? 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6 indexes in y and x direction, right? So can you tell me what is the index of this point? How I should write down the unknown function? It's u 5 and 6, right?
Yeah, the index. Yeah, okay.
Okay, so we're gonna start from 1, right? These are our physical point up to 5. These are our physical grids. And then we're gonna add one more grid for, the ghost points. This is for forward, right? And now let's imagine I have the same grid, but then this time I'm gonna make a backward scheme. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Because this is backward, I'm gonna need some ghost points on left and some ghost points below my domain, right? So I have to make my unknown function even for the ghost points. Can I start from 1 and 1? Of course not, because I'm going to miss this point, right? So what I do is to just shift all these indexes by 1 point. So this time this will be my 1, right? And this is 2, 3, 4, 5, 6. And also the same thing for y direction. So this will be my new index for the y direction. 1, 2, 3, 4, 5, and 6. So I did just some simple modification to be able to define this in MATLAB.
Okay, so that's why, because we're limited by the MATLAB, nothing else.
Exactly.
Yeah, thank you.
Exactly. So for marching for backward method, that's why I actually started to march from 2, right, to the very end. So this 6 here, this is my nx plus 2. For forward method, for marching on the physical points, I need to just march from 1 to nx plus 1, right? For the backward, I need to start from 2 to nx plus 2. However, the number of grids will be the same. Good. Okay, so it's 6:50, guys. Let's just have a short break, and then we're gonna continue at 7 p.m. And if you have any question, I will be online.
Dr. Mahabadi,
Yes, go ahead.
can you please open up your script again by the
Sure.
FDM approximation?
Sure. Yeah, just a second.
Thank you.
Is it fine, or you want me to go down a little bit?
Yeah, right to the approximation part. That's where my script is going wrong. Thank you.
Okay. And if you like, you can actually share a screen, and maybe I can help you.
Okay, yeah, I'll do that.
Okay. This is backward scheme. Okay, 1 to 2. True. Everything looks good. And then you're marching in space. You're starting from 2 to nx plus 2 and 2 from ny to 2. This is fine.
Okay, that's what I couldn't find the unmute. Yeah, but like when I run it, it doesn't make the figure move.
Oh, I see. Okay. And you have the shore graph as well. Okay, this is a little bit strange. But
Yeah, because
can you?
I was fine.
Okay.
Sorry, I was fine running it to like I stopped it at line 39 to check, and everything was still good. It popped up the figure, but then for the approximation part, it doesn't. It's
Okay,
not working.
can you remove the stop point and run it again?
Yeah.
It's running, right?
Yeah.
But I don't see actually anything on your. I mean, on your command window, you should see the time steps, but I don't see anything.
I know.
It seems that it's not just about the plotting. It's trying to start or initiate the approximation, but it's just stuck. Maybe. Just wait a couple of minutes, I think. Okay. Okay, just to stop your program.
Okay.
And at your line 51, can you go to the very end to the right?
Yeah.
Okay, just put a semicolon at the end, so you don't see all the matrices on the right. I think that will actually use a lot of your RAM for presentation.
I gotcha.
Okay, that's not a problem. That was not a problem. Just stop. Okay, let me see. And can you deactivate the plotting before your loop? There was a couple of lines to plot the first time step. Yeah, just remove those. You don't need it.
Okay.
Let's try again. Okay. This is strange. Did you put a semicolon in front of the show graph line? That okay, no.
Put a semicolon here.
No, you don't need semicolon.
Oh, okay.
What is this MATLAB? Is that the online for MATLAB?
Yeah.
Oh, okay.
Is that the
I
problem?
think maybe yes. Yeah, because
Okay.
this is not super heavy program, but it's a little bit heavy. Okay, so maybe it will not allow you to plot the contour f for each time interval.
I gotcha.
Yeah,
Okay,
yeah,
well
there's
I'll get the other one downloaded now, so and hopefully
Yep.
jump back over there.
Okay, cool.
All right, thank you.
No problem. Okay, so if you're ready, let's continue. Anyway, is there anyone who has some difficulty to understand this code? I hope that this is clear, and if not, just let me know. Email me. We can actually set another time in my office hours to talk about all these codings. But I hope that this is clear. Again, it needs, of course, some practice. So it's not really bad if you have some difficulty to understand some of these lines. It's understandable. Okay, let me actually teach you some cool stuff. In any of my, in any of the assignments after this or your projects, we're gonna simulate something. It's gonna be mostly in 2-dimensional or 3-dimensional view. Okay. So you have to present your results, of course, because this is a time-dependent problem. The best way to present this is some cool video, right? So let's see how we can actually record these videos. We just plot them, right? But we couldn't get any video. So let's see how we can write just simple code to get the video out of the MATLAB. So this is how you can write the code to record the video. We're gonna just define a function. It doesn't matter anything that you would like. I'm gonna just name this as video. Then you have to write this script, video writer. So video writer will initiate writing this format for video. In parentheses, you're gonna just name your file, right? Let's say 2D advection problem, right? And then, okay, 2D advection. The format, let's define the format. Let's say AVI, right? This is the format for video, and semicolon. So this will initiate writing the video. You have to open this video. Next, this is the next script. And then once the video file is open, then you can put your plot in terms of different frames into the video, right? So we are adding frame by frame to the video and then recording this video. So this should be before the starting your loop. And then once you plot every contour for each time interval, then that's the time that you can add the frames into the video. Okay, so let's say frame. This is equal to, it will get the frame. These are just some standard scripts that you write to record this video. Get frame will basically get a frame from your plot. So how to get this? You need to write this GCF. GCF means, again, if you don't know anything about any of these functions or variable, just go to the help of MATLAB, and then you're gonna see a lot of information. But anyway, GCF means current frame for the graphic. Okay, so graphical current frame. So it would get the current frame and then return this or put it in this guy. I call this just frame. You can just type FR or anything, it doesn't matter. But these two, this should be exactly get frame and GCF. And what next? Well, we have to put this frame into the video, right? So write video. The first should be this guy, video. So it will open this VID and then put the frame into the video. So again, this is initialization. Open the file, get the frame, and put the frame inside the video. And then at the very end, when everything is finalized, you have to close the video. So let me see where is this function. So I put this in a folder, a special folder, right? Let me see if I can open this folder in front of you. I put it in my desktop. In your case, it would be different place, of course. Okay, so this is the folder that I saved my MATLAB script. And then I'm gonna run my MATLAB. You're gonna see that it will create a video inside the folder. Let me run this. You're gonna see the video. The video is created in my folder, but it's not finished yet, right? I have to wait up to the very end, and once everything is finalized, then you can actually open the AVI file. So let's just wait for a couple of seconds. So if you're wondering how these nice videos are coming from, it's basically from these small, simple scripts in MATLAB. Let's see, what is the size? I don't see the size actually, but it should be increasing, of course. Okay, up to now it's just 0 bytes because it's not closed yet. Okay, so n steps should be go up to, I think, 500. And my suggestion when you actually run this, it's not very heavy. It's a kind of heavy program, is that don't actually put a lot of screens in your desktop because your program may crash. And I hope that my program doesn't crash now. Okay, so we close to go up to 500. Okay. And it's finished, right? So let me see if I can open the video. This is the video. And there are also some scripts to increase the quality of your video. Okay, I don't want to spend more time on this. You can, of course, Google this and find out more scripts to increase the quality, right? The quality is not perfect at this moment. It's not a HD kind of video, but you can actually increase the quality. Okay. Any question, guys? Okay, so I think I need to ask this because you are pretty quiet. Okay, so just type on chat panel and tell me out of 100, what's your score of understanding of this code and everything in our lecture. If you get it 100%, just type 100. If you get it 20%, just put 20, okay? But just put some number, okay? And don't be shy. Good? Yes. Of course. Okay, good. I mean, if it's even 30%, that should be fine, I think, because you need to do practice, right? Okay, but these are actually really good numbers. Okay, thank you. Let me stop sharing, and I think it's now the time to work on higher order of simulations. So up to this point, we just worked on advection problem. It means that the derivatives, it's just in the first order, right? But most of the problems we're gonna need to approximate for higher orders of derivatives. Okay, so stop sharing. Sometimes it's really confusing. I have actually 4 monitors in front of me, so I don't know which one I have to move from the other. Okay. Those points. Cool. And this was my example. All right, so what would happen if I have some problem which involves, for example, advection diffusion problem or Laplace equation, right? So up to this point, everything was just based on one-dimensional advection problem or 2 advection problem. It means that all these derivatives are in terms of first order, right? Just y, x, or time. But then what about the case in a problem that we have second order derivatives? And this is basically the case for most of the applications, right? For example, diffusion equation or advection diffusion. Actually, most of the equations, right? Laplace equation. So all these equations are involving some second order derivatives, and we have to approximate those second order derivatives, right? So for example, Laplace equation, if you remember, we had these u second order derivatives with respect to x plus u y equal to a function or some constant, right? So we need to think about these second order approximations. I'm going to use just Taylor series. And then let's see if we can approximate just this guy, uxx. Let's say our unknown function is just a function of x. One dimension, even it's not time dependent, right? Very simple approximation. So let's work on forward approximation in space. Let's see if we can write Taylor series. So u at x naught plus just a point close to my x naught. This can be approximated by u at x naught. I'm just writing the Taylor series, right? And then truncating this at the second order or the third terms of the Taylor series. So delta x times ux to x naught plus this should be delta x power 2 divided by 2 factorial uxx time x naught. And then the other terms, right? But I will just truncate this up to this point. So I have to find a way to find approximation for this guy, right? So from this equation, you can see that if I rewrite everything based on uxx, I'm gonna need to approximate this ux as well. And this is not good, right? Because we are not sure about the approximation of u with respect to x. So this is actually a trick that we can do. So if you remember, for central approximation for first order, we performed a backward approximation and truncating this at the second order, right? This is what we did before. Let me do a backward approximation again. So this should be x naught minus delta x. These are all the same thing. However, because we basically substitute delta x with negative delta x, this should be negative. Because this is squared, it should be positive. So no impact on the second term. Okay, so for central first order, if you remember, we subtract these two values from each other, right? I mean, forward and backward. And why we did this? Because our intention was to cancel these two terms, right? And then just focus on the first derivative. But what would happen if I basically sum these two values? The forward approximation and backward approximation. So in this case, we're going to cancel first derivative, right? And everything will be based on this second derivative, which is our point of interest, right? So summation of forward and backward approximation of Taylor series truncating a second order. And if I sum these two values up together, this is a final term. So I'm going to have u x naught plus delta x plus this guy, right? U x naught minus delta x. This should be approximated by these two values will be summed. So 2 times u x naught. These are canceled with each other, and then this will be 2 times of one of these variables, right? So 2 factorial is equal to 2. So at the end, it should be just delta x2 uxx at x naught. So this is the point of interest. If I rewrite everything in terms of the second order derivative of u with respect to x, then the approximation of uxx will be equal to, I'm just writing the equation for this, right? And this is interesting. U x naught plus delta x minus 2 u x naught plus u x naught minus delta x divided by delta x power 2. So what this scheme called? We call this symmetric second order approximation. And why symmetric? If you look into the equation, we're going to need a point at the center. We're going to need a point on the left, on the right side, and a point at the left side. So that's why we call this symmetric. And then this should be divided by delta x power 2. Okay, so let me take a copy of this equation. Go to the next page. If you need more time, please type on the chat panel. Okay. So this is our equation for second order approximation. And if I write this in terms of discretized form, uxx will be equal to u. Can you help me to write the equation, discretized form? U, this should be I plus 1. What would be the next? I'm still waiting, guys.
UI.
right? 2 times ui, and then the last one, I minus 1, right? This is just for approximation of u with respect to x, right? So if my unknown function is a function of time, x, and y, this is more general form. This is a 2D form, right? My discretized form of an approximation in forward would be u, I plus 1, I have some j, this should be n. So these two variables would be constant because I'm just approximating on x, right? Minus 2, u, I, and j, n. And this is should be backward in x, right? So I minus 1, n, and j divided by delta x, 2. So this is a general form of the 2D approximation of a second order derivative with respect to x. Any question? Okay, let me take a copy. So in a 1D dimensional problem, what does that mean? It means that if I have my unknown function at t equal to n, and then I would like to predict this at the next time interval, let's say t equal to n plus 1, and I would like to predict uxx at this point, I need to have this point on the left and on the right, correct? This is all I need, and this is symmetric second order approximation. So for the same thing for y, I can write the same equation. However, the approximation should be on j index, right? So j plus 1 minus 2 u, this should be the same. This is the center, right? Plus u approximation on j, so j minus 1 divided by delta x. This should be delta y, right? So this is approximation with respect to y. Okay, so let's see if we can write this diffusion equation. So what is diffusion equation? Unknown function, first derivative with respect to t equal to some coefficient. This k is actually a coefficient of constant diffusion. Okay, we're going to talk about this. Times u xx plus y u second order to y, right? So the difference of diffusion, pure diffusion, and pure advection is, well, time. This is first derivative. However, for the space, in diffusion equation, we have second derivative. Okay. So let's try to write down the diffusion equation in terms of discretized form. How to discretize this? Well, we have how many terms? 1, 2, 3. The first term is first derivative, right? Okay, guys, you have to actually tell something. How I should write discretized form of u with respect to t.
Okay, you can un plus 1.
N plus 1, exactly.
Right. I and j.
Nice.
Minus 2 uijn.
Exactly. Divided by?
Delta t.
Great, thank you. Exactly. So this is first derivative, right? And we already talked about forward approximation. So in time, we're going to use ft. For second derivative, we have two terms, and we have to use this symmetric second approximation. And these are the equations, right? I already have it. So we have to just replace all these first derivative, second derivatives with approximations, right? So let's do this. I'm going to just borrow this. I don't need the entire thing, right? This is just for uxx. So this is my ut, right? This is equal to k times this guy. This is my approximation for uxx. Plus another k times approximation for y. Make sense? And right, actually the one-dimensional advection, here we have a 2D diffusion problem. And out of all these variables, which one I'm interested to predict? It's this one, right? This is my unknown function at the future, n plus 1. So I have to rewrite all this equation in terms of this unknown function. So let's take a copy and move to the next page. I'm rewriting everything in terms of this variable. At the end, your u, I, and j at the next time step will be equal to u, I, j, and n. Actually, I moved this one to the right side. Plus, let me get back one more slide down right here. This form of the equation for diffusion that I wrote is a special actually case, right? In reality, this coefficient of diffusion would be different in x and y direction. This is exactly like the velocity field in advection, right? So the general form would be actually ut equal to the coefficient of diffusion in x times uxx plus ky at y at uyy. And what does this mean? The coefficient of diffusion actually is talking about how fast a concentration or pollution will actually be diffused in time. And the unit of this k, or coefficient of diffusion, is square meter per second. This is a unit. So this first variable, this should be k, and this is ky, coefficient of diffusion in x direction and y direction. Okay, so if I write down the entire thing for a non-function in the future, this will be kx times delta t divided by delta x to the power 2. So I actually move this under my k, and you see that this is pretty close to what we had in diffusion. In advection. In advection, we have velocity delta t divided by delta x, right? So here it's a little bit different, and this is actually our amplification factor. Okay, so in the bracket I have u, I plus 1 and j, and minus 2 u, I and j, and plus u, I minus 1 and j. And almost the same thing, but everything in y-axis, right? So this should be ky, delta t is fine. I should have delta y, the power 2, and I need to modify the indexes. This should be I, j plus 1, I and j, I, j minus 1. So it's very actually similar to two-dimensional advection with some differences. So let's see what would happen in this case in terms of the graphical representation. Let's work on our grid, okay? So let's just make a simple grid. At the first time step, let's say this is t equal to n, right? This is I index and j index. I should have exactly the same space grid for the next time interval. This is at t equal to n plus 1. And I would like to approximate my u, I, and j at this time interval n plus 1, right, from the previous time step. So can you tell me what points I need to predict this unknown function at this time step?
Yeah, the same point and then 1 point each of the adjacents.
Exactly. So I need 1 point from left, top, right, and below, right? Just look at this equation, right? This guy, this is right in the center. So I'm going to call this C, right? I need a point on the right-hand side. Let's call this R. This is again in the center. This is in the left. So I call this L. And on the last term, this is above, center, below, right? So A and B. So I need 5 points in the previous time steps to predict my unknown function, right? Or let's say in three-dimensional view, this should be something like this. I need these 5 points to predict my unknown function in the next time step. Okay, so one more question. Using this symmetric second order approximation, what are the ghost points I need for the simulation.
I think from all directions outside. Right?
Exactly. Thank you. So we're gonna march from this point, and go to every direction. So for this point, I need all these 5 points, right? So it seems that I need, this is the first ghost point, this is the second, and for the rest, I need all these points. So everything around my boundaries, I need to have the ghost points. So this is a little bit different from what we observed for 1D or 2D advection problem, right? So for diffusion, all around my boundaries, I need the ghost points. Okay, so it's already very close to 7:45. I really encourage you to, I think you should practice to write the code for 2D advection. And up to this point, you have all the information to create your MATLAB toolkit for even two-dimensional diffusion. So let's, after our lecture today, I would like to encourage you to work on the same problem, right? Create a 2D pure diffusion MATLAB code. Everything should be same. You have to change your approximation, modify the system for the ghost points. And then for the coefficient of diffusion, let's just use, let me see. Let me open my MATLAB file. I already created this MATLAB file. So, okay, 2 square meter per second and ky equal to 2. And everything will remain the same, okay? You don't need the velocities, of course. These are for two-dimensional pure advection. So if you can write this code for the next week, that would be great. And if you like, you can share actually your results at the beginning of our lecture. They're gonna be some extra points for those that can actually create this MATLAB file. Okay. Any question? Okay, so I'm gonna upload the video and I will try to basically clean all the notes and also upload it on the Brightspace. Sounds good?
Sounds good.
Thank you, guys. Thank you. So if no question, then see you on next Thursday. And don't forget to submit your assignment.
Thank you.
Thank you. Have a good night. Have a good night. Thank you. You too.